Hello everyone, my name is Alexandra and today my team and I will be presenting our project called Quantum Optimization for Ancestral Recombination Graph Inference. So before I go into my part, I want to give a quick idea of why we're doing this and what problem we're actually trying to solve. In population genetics, researchers try to reconstruct the history of DNA. Basically, who came from who, how lineages split, and especially how recombination happened across generations. That's what an ARG, or Ancestral Recombination Graph, represents. It's basically the most detailed ancestry map you can create. Because instead of just showing a tree, it also shows all the points where DNA switched or recombined. The issue is, these graphs get extremely complicated extremely fast. Every time a recombination event happens, the number of possible histories increase. And classical algorithms start to struggle with accuracy or they take way too long. Some tools scale well but lose precision, while others are precise but take forever. So our project is exploring whether quantum optimization, specifically QAOA, can handle this problem better. We want to see if quantum methods can let us explore more possibilities at once and hopefully get to a minimal ARG, the version of the ancestry with the fewest recombination events. That's the overall motivation behind everything we're doing. Now to summarize the project a little more formally. An ancestral recombination graph represents how DNA lineages split and recombine across generations. It's very important in biology because it helps researchers understand population history, mutation patterns, and even how certain genetic traits spread. But actually, building this graph from real data is extremely challenging because of the exponential numbers of possible recombination events. That's why even the best classical programs sometimes make simplifying assumptions. They kind of take shortcuts which can reduce accuracy. So what we're doing is taking this biological problem and turning it into an optimization model that can be run using quantum methods. We take phase genomic data, convert it into a QUBO or Ising formulation, and then run it through the quantum approximate optimization algorithm. QAOA lets us explore a lot of potential ARG structures at once, and the goal is to identify the one with the fewest recombination events, which would be the minimal ARG. So this project is really about combining genomics with quantum computing to see if we can handle a problem that's been historically difficult to scale. And now my teammate will mention the proposed solutions.
Hello, I'm Brandon Niven, and on this slide I will outline the functional description of our proposed solution. Our approach centers on developing a quantum optimization system designed to construct minimal ancestral recombination graphs, or ARGs, using the quantum approximate optimization algorithm, or QAOA. Our system begins with phased genomic data, which we convert into a quadratic, unconstrained, binary optimization model, or QUBO. This QUBO formulation captures the possible recombination events and structural constraints that define a valid ARG. Once the QUBO is constructed, we transfer it into an Ising Hamiltonian, which is the form required for execution on a quantum circuit using QAOA. Another important part of this system is that we combine both quantum optimization and classical optimization techniques. The quantum component, QAOA, is responsible for exploring a very large solution space by evaluating many possible ARG configurations simultaneously. Through repeated sampling, QAOA will start to achieve configurations with lower energy, which correspond to ARGs with fewer recombination events. The classical component evaluates the bit strings returned by the quantum circuit. It assesses whether the current QAOA parameters are guiding the algorithm toward a lower energy solution. Based on those evaluations, the classical optimizer updates the parameters before the next iteration. This iterative hybrid loop allows the system to converge towards the optimal ARG structure. Now I'll go over usability for our project. This system is designed so that users can run the ARG inference code without needing to understand quantum mechanics or the details of QAOA. Users begin by providing synthetic or real genomic data, such as the phased haplotypes dataset from the 1000 Genomes Project, which will be our approach. The system accepts these inputs in standard formats, allowing flexibility in the type of genomic information analyzed. Next, we allow configuration of several key parameters through command line arguments. Users can optionally specify QAOA depth, noise settings, dataset options, and more using these parameters in the command line when running the code. This makes the system adaptable to both experimental and real-world research settings. Lastly, the entire pipeline is executed on the HPC cluster, which handles the computational load required for quantum optimization. Assuming that users have gained access to the cluster, they can submit their job and receive logged outputs that include measured bit strings, energy levels, and the final inferred ARG structure. These outputs will provide a clear understanding of how the model got its solution.
Now going on to the system overview, as you can see, this diagram shows the full workflow of the QAOA process for ancestral recombination graph inference. We start with the input data, which can come directly from online phage genomic datasets. That data is converted into a quantum unconstrained binary optimization problem, and then translated into the Ising model so the structure can be run through the quantum circuit. This process essentially takes the biological problem and rewrites it into a mathematical form that a quantum computer can interpret. From there, the quantum circuit begins with initializing the states and creating superpositions to explore all possible configurations. Then we apply a sequence of QAOA layers, from 1 all the way up to p. Each layer alternates between a cost Hamiltonian, which evaluates how good each state is, and a mixer Hamiltonian, which helps the system explore new possible solutions. These alternating steps are what guide the system toward the most optimal ancestral recombination graph. After the last layer, we perform a standard basis measurement. These results go into the classical processing stage, where the outputs are sorted, organized, and analyzed for their probability distributions. Higher probability solutions represent better ARG configurations. If the objectives are met, we'll stop. But if the solution isn't good enough, a classical optimizer adjusts the parameters and sends them back into the quantum circuit. This loop continues until the model converges. Overall, this structure shows how the quantum and classical parts work together as a hybrid system.
My job in this project is to build and prepare all the data that enters our optimization pipeline. Basically, everything that happens in the model, the QUBO, and the quantum circuit depends completely on whether the data is clean, formatted properly, and usable. So I'll handle a few major responsibilities. First, I either create synthetic datasets or process real-phase haplotype data from the 1000 Genomes project. The raw data often comes with missing values, unphased SNPs, or inconsistent formatting. So part of my work is cleaning and validating it before it reaches the next subsystem. Second, I convert all of that into binary matrices. These matrices are what feed into the QUBO and Ising models. So the formatting has to be extremely precise. Every allele is translated into a 0 or a 1, and the dimensions of the matrix have to match exactly what the model parameter subsystem expects. Third, I check for common data issues, things like mismatched SNP counts, missing values, or incorrect structuring. If even one part of the matrix is off, the QUBO model won't compile and the QAOA circuit won't run. So my subsystem is basically the foundation of the entire pipeline. If the input is wrong, everything downstream breaks. That's why one of my biggest challenges is making sure the real-world genomic data, which is naturally messy, gets transformed into something clean enough for a quantum optimization model. On top of everything, I'm also responsible for confirming dimensionality, formatting documents, and ensuring the matrices are accessible to the HPC cluster for large-scale testing. So that's my part of the project. Building the data foundation, that's the rest of the system depends on. I'll now pass it on to the next team member, who will explain how those matrices get converted into the QUBO and Ising formulations that drive the quantum optimization process.
Hello, Brandon again. On this slide, I will explain the model parameter subsystem, which is the component I'm responsible for in our project. The model parameter subsystem defines the mathematical structure of the QUBO and the corresponding Ising Hamiltonian. As shown here, this involves defining necessary constraints, determining decision variables, and constructing the cost terms that penalize recombination events and therefore allowing valid ARG structures. One of the main challenges listed here is the correct encoding of constraints. In QUBO-based optimization, every constraint must be represented using binary variables and penalty terms. If any constraint is encoded incorrectly, the optimizer may return a mathematically low energy state that does not correspond to a valid ARG. Ensuring proper encoding is therefore essential to maintaining biological accuracy. Another challenge is balancing penalty weights. Penalty terms must be tuned carefully. If a penalty is too large, it dominates the optimization and restricts exploration. If it is too small, the quantum optimizer may violate constraints in favor of reducing recombination counts. Finding a good balance between these is a critical part of my subsystem. All in all, I am responsible for defining the full set of constraints, selecting and structuring the decision variables, and finalizing the QUBO and Ising Hamiltonian used throughout the QAOA process. This will ensure that the overall formulation accurately captures all of the requirements for minimal ARG inference.
Hello, I'm Ellen Farafonov, and I am responsible for the Quantum Approximate Optimization Algorithm Subsystem, or the QAOA subsystem. This subsystem includes the building of the QAOA quantum circuit using the Qiskit Python library and defining the Hamiltonians. This circuit is comprised of the quantum circuit as well as the classical processing system. It takes in the Ising model formed from the input data, and then it goes from the initial states, it goes to the superpositions, which are then inserted into the p-layer loop of the QAOA layers, which begins with the finding the cost Hamiltonian for each state, and then the mixer Hamiltonian for each state, and this is repeated for p number of layers, which is the reason why it's called the p-layer loop. Then after, the standard basis measurement for each state is taken, which is then used for classical processing. And in the classical processing, the results get organized and the probabilities get sorted, and it checks if the objectives are met. If they are met, then the QAOA system is done, and it sends it to the next subsystem, the results subsystem, for the results to be processed and for the graph to be formed. And then if not, then the solutions and probabilities get taken through the classical optimizer, and the parameters are updated for the whole process to repeat again until the objectives are finally met. So this subsystem performs measurement sampling, and challenges of this include circuit implementation. It's a complicated problem, and it is hard to get the most accuracy without error. And noise is also another challenge, as noise could also impact the accuracy, and errors can arise from the noise, the quantum noise, which makes the optimization difficult. Another challenge is convergence behavior, which is dependent on the choice of the mixer Hamiltonian, and also the circuit depth that could impact the accuracy of the QAOA subsystem. Overall, I am responsible for constructing the QAOA circuit and implementing the cost mixer Hamiltonians, as well as the configuring the loop for p-layer.
Hello, my name is Namira Ali, and I'm responsible for the results subsystem in our project. In my part of the project, I focus on this stage of the system that takes the raw bitstring outputs produced by QAOA and turns them into something that we can actually evaluate and interpret. After the quantum circuit completes its run, it generates a distribution of possible solutions. My role is to extract those distributions, analyze which configurations have the highest probability, and then determine whether the model is converging toward minimal recombination structures. A major challenge here is distinguishing meaningful solutions from noise. Not every frequently measured bitstring corresponds to a biologically valid ancestral recombination graph. So my subsystem produces the visualizations, probability plots, and numerical summaries that allow us to compare the QAOA outputs to its expected baselines. This feedback loop is really essential because it tells us when the algorithm is behaving correctly and when parameters need to be adjusted before running the next iteration.
Hello, my name is Diego, and the component that I'm responsible for is the Real Data Processing subsystem. So my role focuses on taking real genomic datasets and converting them into matrix formats that are fully compatible with the rest of our model. These matrices need to align with the structures expected by the QUBO and Eyasync formulations so that they can move to the quantum pipeline without any issues. Because real data is more variable than synthetic data, this subsystem also involves adjusting constraint weights to account for biological noise and natural structural variation. This helps keep the optimization stable and prevents the model from misinterpreting irregularities in the dataset. Some of the main challenges include handling noise, dealing with structural variance, and making sure the dataset matches the exact input format required by the model. Overall, I'm responsible for gathering real genomic data, reformatting it to meet the model specifications, and comparing the outputs against a synthetic pipeline to confirm that the system behaves consistently across both data sources. And now for the system integration, or just how all of our subsystems work together as a whole. Across the full pipeline, we need to make sure the input data, the model parameters, the QAOA implementation, the results subsystem, and finally the real data subsystem all connect seamlessly. Even though each component is handled by a different person, the final system behaves as one continuous workflow, so consistency is extremely important. Integration mainly focuses on confirming that every component uses compatible matrix formats, encoding styles, and parameter structures, so that information flows cleanly from one stage to the next without requiring major reprocessing steps. This becomes even more important once we move to real genomic data, because even small inconsistencies can cause the quantum or classical parts to behave unpredictably. Some of the biggest challenges here are runtime, memory scaling, and debugging. As datasets get larger or more realistic, these challenges naturally increase. Part of our ongoing work is not just connecting the components, but also identifying where bottlenecks occur and planning how to optimize the flow moving into the next semester.
For the past month or so, my team and I have been deeply focused on building the foundation for this project. So that includes learning Qiskit, understanding the basics of QAOA, reviewing prior haplotype phasing code, and brushing up on the biology behind ancestral recombination graphs. This early phase was critical to us because everything that we do later in the pipeline depends on getting those fundamentals right. From there, our schedule transitions into subsystem development. Each component has its own deadlines. We have from generating synthetic input data, to defining the model parameters, to constructing the QAOA circuit, and then the results analysis subsystem. After all these core pieces are completed, we move into the real data processing, and then full integration and testing it on the HPC cluster. The final stretch of this timeline is focused on optimization, documentation, and just preparing the final paper and presentation. Overall, the schedule is structured so that each major milestone builds logically on the work that's completed before it. After our presentation, our focus shifts towards strengthening and refining the system. The first step is extending our testing by using larger matrices. This helps us understand how the pipeline scales and whether any parts of the system break down as the data size grows. From there, we move into refining the penalties in our QUBO model. These penalty weights directly influence how the optimization behaves, so tuning them is important for making sure that the algorithm consistently converges toward valid and minimal ARG structures. Once those adjustments are made, we'll rerun the entire pipeline with real data again. This time we're going to incorporate everything that we've learned from the earlier testing phases, which is going to give us a more realistic view of how the system performs outside of a controlled synthetic condition. And then after that, it's all just about cleaning up the document, organizing it, tightening the code base, and just preparing everything for our final integration. And all of that leads up to our official project completion on May 1st.
For the early prototype implementation, so far, we have been working on the quantum approximate optimization algorithm and ancestral recombination graph research. That is something that we have started from the beginning and have been continually doing to have the best results for our project. We have created the initial synthetic haplotype matrix that was provided by our mentor, and we have been running the code and seeing how it works and determining the limitations of it for it to help us develop the QAOA. The haplotype phasing code is also the input for the ancestral recombination graph system, but we might not use the code that we might not use the code that we did on the data. We might just use data from the 1000 genome dataset. We also are in the process of the QUBO constraint formulation. We have been working on that. We're going to finish that really soon, hopefully this month. And we have completed the block diagram and state diagram. The block diagram is in this presentation, and the state diagram is in our proposal. And we have defined the pipeline flow of the systems and have a solid plan of what we're going to do. So features that we still have to implement is the full circuit completion. We still need to complete the whole QAOA circuit, and we're working on the input data and the QUBO right now. So we still have to finish that before running the full circuit, processing the results, and working with real data. We still have to work on formatting the output as well, all the ancestral recombination graphs that will be provided by our code. We need to figure out how to format that, and we still need to do that, and how to organize the results. And we need to integrate real data into our circuit because we've been working with test data. The data that we've been using to run the haplotype phasing code was all test data, and we're probably going to first do test data for the ARG system as well. So we need to work on real data integration. Those are things that we still need to implement and will implement by the deadline.